Now, I know I said that like basically capacitors and inductors become resistors, but then to avoid confusion, we have to have different names for these imaginary and complex resistances, right? So I'm going to define something called impedance. So I'm going to call impedance, I'm going to show impedance with Z and say Z is equal to R plus JX. So Z being impedance, R is our known value, which is resistance, our known variable, and X is, well, I'm going to call it reactance. Okay, so I'm going to say that every component could have an impedance. Impedance is basically of the same nature as resistance. You can say it, you can tell that from the name, right? One of them is resisting against something, the other one is impeding against something. So they're kind of synonyms, right? Resistance means, well, a real resistor. Impedance means, well, my resistance or impedance has, well, both real and imaginary parts. The real part I'm going to call it resistance. The imaginary part I'm going to call it reactance. So now for real resistors, I know that the impedance becomes R, right? So this is basically for a resistor, I have an impedance equal to R plus J0, meaning that, well, it doesn't have any reactance, it doesn't have any imaginary part. For an inductor, the impedance is 0 plus J omega L. So it has no resistance, but it has, well, omega L reactance, right? It's all imaginary. And for a capacitor, I can say that Z is equal to 0 plus 1 over J omega C, right? Now, since J squared is equal to -1, so basically 1 over J becomes negative J, right? Or yeah, so basically J times negative J becomes 1. So that's why 1 over J, I replace it with negative. That's why I call reactance of this guy is -1 over omega C. The important thing is for inductors and capacitors, I only have reactance. I only have imaginary resistance or imaginary part of the impedance. And for resistors, I only have the real part. Now, if I have a network of different resistors and capacitors, you can imagine resistors, capacitors, and inductors, you can imagine that I might have a component that I'm going to show it with just a box because it's just a rectangle because, well, it's not resistor or inductor or capacitor, so I have to define a new symbol for it. And this component might be 2 plus 3J, meaning that it has both resistance and reactance, right? So when you combine a bunch of impedances together, if you're only talking about resistors, inductors, and capacitors, the impedance is going to be purely real or purely imaginary in the case of inductor and capacitor. But when we're talking about a combination of all of these together, as we will see in the examples, you might actually have complex impedances which have both real and imaginary parts. Okay? Now, if you convert all your components, meaning resistors, inductors, and capacitors, into impedances, then the good news is that KCL, KVL, series and parallel combinations, Thevenin and Norton equivalent circuits, and source transformation, whatever else that you have learned about resistive circuits are applicable to impedances with phasor when we're doing phasor analysis. Okay, so there's nothing new to learn here other than, well, practicing. So basically, you're going to be doing the node voltage or mesh current analysis, you're going to be doing source transformation, you're going to be doing Thevenin and Norton, whatnot, right? You're going to be doing all of these stuff as if you have all resistors. And what changes really is that, well, instead of real value resistors, you're going to be dealing with imaginary and complex value resistors. Okay, so the math is a little bit different, but the procedure from the circuit analysis point of view is identical.